So, chapters for today, I guess I'll say right now, like you should, for next week, you should look at chapter 18. We'll probably spend most of the week on 18. I don't know if we'll go any farther than that or not. I've put up on the board sort of what was on the board at the end of the last class. So as a reminder, the nanometer values here are lambda maxes, so the wavelength that is best absorbed by the molecules, basically what that's saying. And again, 174, 217, 258, these are all in the UV. All right, so you and I would not look at these molecules and see any color. We would think they all look the same. But if you had a spectrometer, or if you could see in the UV, they would look different. They would have different colors. All right, so, and as an example, here's a molecule that I thought I had more space than I did. All right, so this molecule has a lambda max at 452 nanometers. That's now in the visible, so we can see that. Like that molecule absorbs light that we see. And again, and it's complicated. This is not a spectroscopy class. We do some spectroscopy, but it doesn't only absorb 452. That's the wavelength that is maximally absorbed. So it's got a band. It absorbs down into the UV. It absorbs out close to 500. That's blue-green light. So this molecule absorbs blue-green light. So what color do you think it is?
Yellow.
It's reddish, yellow, orange. This molecule is beta-carotene. All right, so you've maybe eaten this today or in the last week. You find it in tomatoes and carrots and stuff like that, and it's yellow and red. The other thing that's kind of cool about this, so I guess the other thing to show first before I do that, the more conjugation you have, the more double bonds, pi bonds you have conjugated to one another, the more red the molecule is going to absorb. All right, so generally speaking, the more conjugation we have, so more conjugated pi bonds equals a red shift in the absorbance, and usually a more intense absorbance. Like I said, this is not a spectroscopy class. I don't want to spend too much, I desperately want to spend a lot of time on it, but I'm not going to. All right, so the more conjugated double bonds you have, the more redshifted the absorbance. So how does bleach work? If I spill something on my shirt, which I do fairly often, I put bleach on it, like the color goes away. How does that work?
Probably takes away all the conjugated bonds.
Doesn't take away all of them, but it takes away a lot of them. So bleach, in fact, if you, all right, so I'll do this one up here just as an example. Bleach actually makes in situ, so bleach is not chlorine gas, but it makes chlorine gas. And so you guys can see how this would work, right? This might give us, right, so Cl2 will add across double bonds. And so if you have a molecule that's got a bunch of conjugation in it, and you break up that conjugation, then you will, if you break up that conjugation, then you'll kill the absorbance, right? So again, hexatriene is invisible to us, but here we have 3 conjugated double bonds. In this product, we have none. If you chlorinate the ends, you might have 2. But yeah, that's basically it. So you want to oxidize the double bonds. Bleach will do this. Bromine, iodine. There's a lot of things that will do it. All right. The other thing that lambda max means, and maybe the thing that I saw some, I don't know, I don't want to say confused or glazed eyes at the end of the last class, but these molecular orbital diagrams, right? If I have one pi bond, I've got one pi bonding molecular orbital with 2 electrons in it. That's kind of the definition of a pi bond. The hard thing I think most of you get that. The next thing that's maybe a little harder to get is that every bonding orbital has a corresponding anti-bonding orbital. Right? So if you see one pi bond, that's got to be one pi bonding orbital and one probably unfilled pi anti-bonding orbital. All right. And this absorption, what is the physical change that takes place in molecules when they absorb visible light or UV is an electron being promoted from a bonding orbital, or sometimes like a lone pair, maybe, a non-bonding orbital, up to an antibonding orbital. That energy gap tends to correspond to ultraviolet light, visible light in organic molecules. Okay, so you guys have seen a lot of spectroscopy at this point. You've seen infrared spectroscopy. When a molecule absorbs an infrared photon, it changes how it vibrates, right? The physical change in energy in the molecule that equals the photon that's absorbed is a change in vibration. In NMR, the physical change that is associated with the radio photon is a change in how the nucleus is oriented in a magnetic field. Microwaves change how the molecules rotate. So when you guys nuke your burrito, you're changing how the water molecules in the burrito rotate. Okay, so UV and vis absorption is an electron changing orbitals. Like I said, this is not a spectroscopy class, but I'd like you to start thinking about that. The other thing the important lesson that comes out of the last class is that for a lot of chemistry, the dominant interaction is a HOMO-LUMO interaction. So we call these frontier molecular orbitals, right? The highest energy orbital that's occupied, that's the HOMO, highest occupied molecular orbital, and the lowest unoccupied orbital, right? The highest occupied orbital, those are the electrons that if a molecule is going to give them away, those are the electrons you're giving away. All right? And if a molecule is going to accept electrons, they would go into the LUMO. Right? So if I take hexatriene and I add electrons to it, like I actually plug it into the wall outlet and I just flood it with electrons, that electron would go there. If I put them on the cathode, if I hook hexatriene up to the cathode and I take one away, I would take that one away. Right? The most reactive electrons in a molecule will be in the HOMO. The most reactive unoccupied orbital, the place where electrons go, is the LUMO. And we're going to see that. Like I said this at the end of the class last time, but I want to start there again. You guys have done nucleophilic, electrophilic chemistry, right? So a nucleophile has electrons. It's giving electrons away. So you would see a mechanism maybe written like this. Right? So the nucleophile is a thing that's got electrons. The electrophile is a thing that wants electrons. This could be an acid and base. So this could be a Lewis base, or even a Bronsted base, and this could be a Lewis acid or even a Bronsted acid. And what's happening is we're going to have two electrons in a HOMO. And those two electrons in the highest occupied molecular orbital are going to be donated to the lowest unoccupied molecular orbital in the electrophile. For a fast reaction, you'd like these two orbitals to be close in energy, or maybe the LUMO to be a little below, right? So if I'm a strong acid, what that means is I've got an unoccupied orbital that's pretty stable. So I've got a place I can put electrons. If I'm a good nucleophile or a good base, that means I've got a pair of at least one pair of electrons quite high in energy that I can give away. All right. I have a feeling this entire video is my shirt. All right, any questions about where we left off? The other thing I did on Monday, I'm going to erase this. So if you're at home, pause it. This is a nice thing to have written down. All right, so for butadiene, let's just take. Actually, I'm going to take all of this off except the hexatriene. So let's just look at 135 hexatriene. Again, nomenclature, you want to have numbers as low as possible. Longest carbon chain, so that's hexatriene, right? There's 1, 2, 3, 4, 5, 6 hex. 1, 2, 3 alkenes, triene. 1, 3, 5. 1, 3, 5. 1, 2, 3, 4, 5. So when you number an alkene, you always want to give it the lowest number possible, right? It's got to be 2 carbons, so you give it the lowest number. All right. So if we look at the molecular orbitals of this, and I know some of you guys were kind of, again, I don't want to say freaking out, but I think you look worried. You look like I'm going to ask you to draw molecular orbitals, and that's not what I'm going to do. But I would ask you to recognize molecular orbitals. Okay, so the most stable orbital will just have 6 p orbitals in phase. All right, so remember a pi bond, is just going to be formed anytime you have 2 p orbitals on adjacent atoms. All right, you guys have seen this. If I put these together in phase, so I do plus and minus. Your book does red and blue, I think. You can also do shaded and unshaded, so we can, shade one of these in, leave these other 2 lobes blank, so the shaded lobes reinforce each other, the unshaded lobes reinforce each other. I'll draw these kind of like a top-down look. So if you're seeing just open circles, you're looking at the unshaded bit. Right? So for all of these polyenes, the most stable molecular orbital, the lowest energy molecular orbital, that is the least reactive, is always going to be just all the p orbitals in phase. The highest one, the highest energy, orbital will be all out of phase. And so I've alluded to differential equations a few times. You can solve equations for molecular orbitals and electron energies, and they look like waves. So that's where we get we describe them as waves. They behave in a lot of ways like waves, right? These are things you cannot see. Technology's come a long way. When I sat where you sit, humans had not taken a picture of a molecule. We now have. It's not easy, but you can do it. We still can't get a picture of electrons. We probably never will, because the electrons are not in one place, right? They behave kind of like waves, behave like particles. You've all heard of the uncertainty principle. We're not going to apply that in here, but it means you can't know the energy and location of an electron at the same time. So we do all this by math. What I'm doing right now is just sort of qualitative. I'm telling you what the math says. The other orbitals in between here, students often get, I get a little lost in how to come up with them. Because like I said, you shouldn't come up with them just out of your head. You should come up with them based on math. This is not going to come up on a test or anything. The molecular orbital, right, this is all shaded, so the actual molecular orbital then, nobody ever throws a marker away. Right, the actual molecular orbital is this kind of fuzzy thing like this. The symmetry of the molecular orbital has to match the symmetry of the molecule. All right, and this is a mathematical thing, but I can't just have like these 2 open, filled, open, 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 because that wouldn't be symmetric. It wouldn't be anti-symmetric. My point is, you don't have to worry about this. I'm not going to ask you on an exam to draw a molecular orbital. What I want you to know is this. If the 2 p orbitals next to each other are in phase, that's a bonding interaction. Or if they are out of phase, right, so that's bonding, that is anti-bonding. I want you to know that. Yep.
When you say they're in phase, does that just mean like the electrons have the same spin?
Not spin, it's actually the orbitals themselves.
Okay.
So, and the weird thing about this, seriously, we can get lost in this, I need to move on. The weird thing is orbitals exist without anything in them. So they're mathematical possibilities, right? Quantum mechanics is very weird. I'm not qualified to teach it to you. But basically I've got two p orbitals and I can put them together. And probably the way maybe in AP Chem or Gen Chem, you know, you were told, you put them together in phase to get a bond. And that's a half-truth. They can mix in phase, but they also mix out of phase. They do both at the same time. And so you wind up, if I take two atomic orbitals and put them together, I have to get 2 molecular orbitals. If I take 6 atomic orbitals and put them together, I have to get 6 molecular orbitals. Right? You can't create or destroy orbitals. Okay, so back over here. It's not, like I said, I don't necessarily want you to be able to draw what they look like, although it'll be a little, I'll use molecular orbitals to explain some chemistry that happens. The other thing is, and this is a conceptual thing you really need to have. So conjugated pi bonds are more stable than not conjugated pi bonds. And it's because when you conjugate them, you get at least one orbital. You get at least one molecular orbital that is delocalized over more than 2 atoms. So any bond is electrons delocalized over 2 bonds. Sigma bond, pi bond, doesn't matter. These conjugated pi orbitals, like in hexatriene, you get one molecular orbital that's spread out over 6 atoms. And again, the more spread out atoms are, or electrons are, the more stable they are. Okay, so you've heard probably since the beginning of organic chemistry, the more resonance structures you can draw, the more stable the molecule is. What that really means is the more you spread out electrons, the more stable it is. Okay, so you get at least one orbital that's a lot more stable. And we can apply some math to this, because I know that's what you wanted. You were just sitting there thinking I was not doing enough math. All right, I'm going to need my paper. So let's look at spelling isn't my strong suit. Draw me the product of that reaction. Or I say draw the product of that reaction on your page. I'm not going to take it up or grade it or anything. All right, so you should remember this from Orgo 1. This is a hydrogenation reaction. And this one, the mechanism of this really doesn't fit most of the stuff we've done. You don't have to know the mechanism of this in this class. You need a transition metal, palladium, rhodium, platinum, something like that. And molecular hydrogen, H2. And the product is just going to be cyclohexane. All right, and I'll draw the 2 H's we add in. They add in cis. That is sometimes important. Well, okay, cool. Delta H for this reaction, delta H, not entropy, is minus 120 kilojoules per mole. So it's negative. Delta H is negative. That means the molecule is actually more stable. All right, so cyclohexane, the bond, just if we consider the bonds, is more stable than cyclohexene plus hydrogen. And the reason for that is we replace a pi bond with a sigma bond, right? We break a pi bond, we break a sigma bond, and we make 2 sigma bonds. So net, a pi bond turns into a sigma bond. Sigma bond is more stable. That is almost always going to be, if replacing pi bonds with sigma bonds, just from a bonding perspective, is almost always favored. Okay, so assume you have a large excess of hydrogen, which you always do when you do one of these reactions. It's really hard to use a molecular equivalent of a gas. So I've drawn 3 more molecules there. Draw me the product of those. You got all the hydrogen you need to do any kind of reaction you want. So draw the product and predict the change in H. Predict delta H. You get the same products out of all of them, right? You get cyclohexane out of all of them. If I add hydrogen to benzene, let's just say, how many of you were told in Orgo 1 that you could not do this reaction? Anybody remember this? Yeah, you were, because I told you.
Yeah. You said benzene is very stable.
Benzene's very stable. Benzene does not, it is very difficult to hydrogenate benzene. So that was mostly because I would give examples, and like I put a benzene on a chapter 8 test, and everybody would want to hydrogenate it, and it makes sense really until this chapter. So I apologize. Well, just you're the only one I did that to. So okay, benzene's hard to hydrogenate, but if you do, you're going to add it here first, right? You can't add 3 molecules of hydrogen all at once. So you would add here, and you get that molecule, right? And then you'd add there, and you do that, and then you'd add again. So they're all cyclohexane. And right here we've got 2 double bonds. Here we had 1, it was 120, so if we got 2, must be 240, right? Turns out it's 239. That's a rounding error probably. Probably not exactly 120. So what's this one?
Probably between those 2.
Yeah, it's a little bit less. It is minus 232. And the reason for that is, so again, you're replacing pi bonds with sigma bonds. So the bonds are getting stronger. Cyclohexane bond, again, just from a bonding perspective, cyclohexane is more stable than 1,3-cyclohexadiene. The reason these 2 are not the same is that these 2 double bonds are conjugated, right? Pi bond, sigma bond, pi bond. In this molecule, they're not. Pi, sigma, sigma, pi. The p orbitals of the 2 alkenes in that second one are not conjugated. So they don't get any added stabilization. They're just 2 pi bonds. All right, so what's the guess on the bottom? Right, you'd predict negative 360. 3 pi bonds, we multiply that by 3, but it's not going to be that low. And in fact, shockingly, benzene's more stable than cyclohexadiene. All right, that's a huge difference, right? There's a little bit of a difference here just for the double bonds being conjugated. But not 8 kilojoules per mole. That's enough. So if you do a reaction, if you ever do an elimination reaction, and you could make one of these 2, you'll make this one. Right? Go back to E1, E2 chemistry. The molecule would rather make the more stable alkene, and that's going to be the conjugated alkene. Right. But this is a completely different ballgame down here. And we call, I think I've shown my ass to the camera. Apologies if you're at home. Or you're welcome, either way. Show my wife this later. All right, so we call benzene an aromatic molecule. So again, think about how science progresses. I'm going at this backwards. I'm drawing you molecular orbitals, and I'm basically telling you, not quite completely modern, right? This is 1950s theory. Still very useful for working organic chemists. The differential equations, if you guys go take PChem 2, you'll hear like 1995 theory. And if you go to grad school and do PChem, you'll get 2025 theory. And hopefully, well, somebody at some point in your life will come up with 2043 theory and it'll be better. But if you think about the way science progresses, like these are molecules, people have been doing chemistry forever, right? Cavemen went and like chipped off rocks and built bronze axes and stuff. They had no theory. And well, they did have theories. They were crazy and terrible, but they knew how to do stuff. Like all of us in this room, including myself, right, who have a lot of book smarts, throw us out on the savannah and tell us we have to build a weapon to fight off a rhinoceros or something, and we probably all die because we have fewer like practical skills like that because we don't have to. We own guns and hire park rangers and B-52s and stuff, so we don't have to do that kind of thing. But people have done chemistry in some form or another for a long time, and so where all this comes from is we learned this empirically. And so people started noticing that, hey, there's a lot of molecules that are really stable. So Markovnikov added HBr to alkenes. Figured out that the Br goes on the more substituted carbon. He would try to add HBr to benzene and it just wouldn't, nothing would happen. Benzene would sit there. All right, so in chapter 18, I tell you how benzene reacts. Benzene will react. If you look at this, so I say that benzene's way more stable than you expect. It's more stable than you expect. But it's still, if you hydrogenate it, it's downhill in energy. Right? Again, you're exchanging pi bonds for sigma bonds. It's a slower reaction, and it's less exothermic than you expect. The other thing I should add here, entropy, right? The other one is entropy. So the total change in energy, that's an equation. The equation I just wrote in green. I don't know if that's, I wonder if it's on the camera. Yeah, it's on the camera. Sure. The change in Gibbs free energy equals the change in enthalpy minus the temperature times the change in entropy. Entropy at a rough approximation is disorder. So the more bonds can rotate, the more freedom of motion. We actually, statistically, we do this in terms of how many states can a system occupy. Right? We are more disordered than if there were two of us. Right? Because there's all sorts of different ways we can be in here. If there are two of us, there's fewer ways for us to be. So here we've got hydrogen. Cyclohexene plus one hydrogen goes to one molecule. Two molecules become one. That's more ordered than it was over here. Two alkenes plus hydrogen goes to one molecule. So three molecules go to one. The change in entropy for these two reactions is basically the same. It's not exactly the same, but it's really close. And here you've got benzene plus three hydrogens goes to one molecule. Four molecules turns into one. So the change in entropy for the bottom reaction is very unfavorable. Again, that's going to be Chem 280. You'll see that a fair amount. I'll probably mention it in this class some.